everyone. Firstly, I'd like to express my highest gratitude for your interest and passion for this topic. Actually, this is my first YouTube video, and I hope you could enjoy it. Today, our topic um, is a brief introduction about the complete process of data mining, data analytics, and data processing by employing several Euro and universal machine learning models, including including classification tree, logistic regression, and neural network. Actually, this three model I will cover them all today. And to achieve this target or to finish this task, I choose the dataset named Diabetes, which is provided by NTU AI Lab. Actually, this dataset contains more than 760 observations, both from healthy people and diabetes patients. To be more specific about some of the typical health and body features. The ultimate purpose of this research or of this project is to employ, is to generate maybe one, maybe several effective classifier and predictor, so that we could predict whether a person will suffer from diabetes or not according to some basic feature of his or her health condition. Actually, after such a brief introduction of our purpose and dataset, I will begin our coding part. Actually, the first step, maybe as every data analyst might do in their Python coding, is to import some very important and significant third-party packages. Here we import NumPy and Pandas. So, bingo, successfully imported. And then we need to import our dataset into this environment. Since the dataset is saved as a file of CSV, we need to employ this function named recsv in Pandas to actually put this dataset into our environment. And after that, in order to guarantee an overall view of the dataset, we need to understand the data structure or data type of each indicator within it. So we use this line of code to guarantee it. Fortunately, the dataset is successfully imported as a frame, and there are and all the independent indicators, all the eight indicators, all the 8 variables are numerical, and merely the dependent variable, the class variable, is object, which means that each element within this column presents as a string. So after acquiring such a general view of the dataset, there's another little trick we need to do, that is to facilitate our further research or the further procedure in this project. So in order to do this, we rename the independent variables and dependent variables. Independent variables as x1 to x8 and dependent variable as our conditional customer as y. So we rename it as this block do and show them. It seems that most of the data are pretty neat, and it is also easy to discover that y actually is a dummy variable with a form of string. So later on, we will turn this kind of string form dummy variable to a numerical form dummy variable as a form like 1 and 0. So after that, we would like to guarantee a further understanding about the features within the dataset. how those kind of data distribute and how they might scatter. Um, Fortunately, as mentioned before, all independent indicators are numerical, so we could simply use the attribute within the data frame named describe to acquire all the to acquire all the features. Here we report eight features of them. Eight basic descriptive statistics of them. They are the total number of observation, the mean value of observation, the standard error, the minimum value and maximum value of those observations, and also the median value, the one false quartile, and the three false quartile. This um, altogether eight features. This is pretty simple, right? So the next thing, as mentioned before, we need to transform the data, the data structure of Y from a series of string to a series of number int. Just transform them into numerical form. So firstly, we define a transform function, and by employing the mapping property of data frame in Python, we apply this nameless lambda function to each element of Y, and after that we can easily calculate the ratio of positive and negative cases. It seems that positive ratio is about 35% and the negative ratio is about 65%. And maybe here comes to the most important and interesting part of our data cleaning process. We need to find some outliers to detect them and to change them with or to replace them with other values. So to put it more bluntly, outliers are just abnormal observations. So there might be many forms of outliers, and here we hold X3 as an instance. Actually, during our observation of those descriptive statistics, this matrix, we found that the minimum value of X3 is 0. When considering the actual meaning of X3 as blood pressure, something goes wrong. To be more specific, if someone's blood pressure is 0, it simply means he or she is dead. But actually, we cannot make any inquiry from dead people, right? So there must be something wrong during the data collecting or processing procedures. So we need to adjust those 0 value with more reasonable value. Here we replace them with the mean value of X3 because it will generate the least increasing of loss function. So just almost same procedure with the former one. Firstly, we select all X3 whose value equals to 0, and then we define a transformation function and apply them to each element of X3 within the data frame. So after that, we show the data frame again. It seems that there are no more 0 value within this column. It is good for our further research. And after that, we come to our final part of data cleaning. It is called normalization. It is of great significance mainly for two reasons. First of all, there are a bunch of machine learning models pretty sensitive to the mean Euclidean distance within, among data points within a data set. If this kind of distance is too high, the performance of classifier like SVM will be pretty bad. But that is, that is not the most important because it has nothing to do with the model we will conduct later. But here's what really matters. There are another bunch of machine learning models whose optimizer are also under the influence of mean Euclidean distance of the data set. To be more specific, logistical regression is just a number of this group. The optimizer of logistic, if the Euclidean distance within a data set is too large, the optimizer of logistic regression will perform clumsy and ineffective. In order to make our regression and training process more smooth, we decide to normalize all this data. So normalize all this data, it just means to put the data in a large range into a small range according to a certain ratio. So here we come to two. It comes two methods. The first method called standard scalar. It is based on standard normal distribution. And second, it is called min max scalar. It is based on the value of the minimum and maximum value of the data set of the variable in the data set. Well, actually, one of the main difference between these two, maybe we should call it normalizer, is that the standard scalar can both generate positive and negative values, but the min max scalar will always generate positive values. To put it more bluntly, the latter one is more convenient and easier to deal with during our further fitting prediction and training process. So we generally use the latter one in our logistic regression. This block of code just realize the function to normalize x to normalize x. There's one thing I need to stress, that y do not need further normalization because there are merely two values within y and it already satisfies our requirement. So we run it. Yes, and show the normalized value of x. It seems pretty good, right? Then we officially come to our machine learning part. Well, actually, this block refers to maybe the most important concept within machine learning. That is the idea of splitting, the idea of dataset splitting. We need to split the dataset into training set, validation set, but actually this set is optional, and testing set. Since the most fundamental idea of machine learning is to train a model from a part of dataset, validate it from by another part of it, and test it from and test it on the rest of the dataset. So when we are given a dataset, we need to at least divide it into two parts: training part and test part. So here we just employ the function named train test split in sklearn. It is pretty convenient, and the dataset we employ is our normalized 1x and our y. Here the test size equals 0.2, which means that merely 20% data will be left as as a test set, and other data will be used to train the model. So here I assign a certain value to the random seed in order to ensure each time of my splitting will come out the same result. So let's begin with fitting process. Yes, splitting successful, and let's begin with the fitting process of our logistic regression model. Well, actually, just as its name suggests, logistic regression is still a regression model which employs sigmoid function as a link function to project the original dataset from 0 to 1. From the maybe I suppose, from the real number field to to the interval between 0 and 1. And if the fitted value is near to 1, then we classify it as 1. And if the fitted value is near to 0, then we classify the final result as 0. So this is the basic idea of it. But considering the fact that we have already do some normalization work before, this kind of the function of sigmoid the function of the effective the effects of sigmoid function could be limited, but it is still effective enough. So and also, as we mentioned before, since logistics regression is still a linear regression model, we need to check out the significance of each variable and to determine whether or not to discard a certain number of insignificant variable under different criterion probability. So here we just import the logic formula from state model, exactly similar formula to the logistics regression, and we fit its model by trend side, trend y, and trend normalized x. So let's see what happened. Actually, iteration it is acceptable, and it is pretty obvious that there are three insignificant independent variables. They are x3, x4, and x8. In order to guarantee the credibility of our model, we need to discard all those variables later and adjust our training set and test set. So that's what we would like to do in this part. Firstly, we import a very important classifier named logistic regression CV. We import this function rather than logistic regression, simply because by employing this one, we do not need to manually split the validation set, and under this circumstance, we can easily realize a tenfold cross validation by set a very simple parameter. And from other procedures are pretty similar. We adjust our x and y, and we normalize our x, and then we split the true and test set. After that, we generate an instance for the logistic regression CV, this classifier, and we feed this this classifier with our trend set mentioned before. And then we would like to test its performance on. We would like to evaluate its performance on the test set. So we put the model on test set, which actually comes out predicted y. So according to the predicted y and the true value of y in the test set, there is a confusion matrix we need to derive from. Actually, the confusion matrix is vital. I mean, it's vital for the evaluation of any classification model in machine learning, because it contains maybe all concept or all components that we could use to organize our criterion in evaluating a model. For instance, here we import 4 scores and 4 scores to evaluate our model, and all components of each score is just in the component of within confusion matrix. Actually, there are 4 values within the confusion matrix. There are the true positive cases, the true negative cases, the false positive cases, and the false negative cases. So firstly, we would like to report the accuracy score, which is maybe the most fundamental and simple score. So actually, it could be calculated by the sum of true positive TP, that is true positive cases, plus Tn, that is true negative cases. over the sum of true positive over the amount of the observation within test set. And the precision value or the precision score actually is aiming at testing the validity predicted positive values. So it could be calculated as follows: TP over the sum of TP and FP, which means the sum of true positive values and the false positive values. And another score named recall score. So the recall score generally tests whether all actual positive values are classified or are predicted as positive ones. So it could be actually it could be calculated as TP over the sum of TP and Fn. So I mean, under this circumstance, the accuracy score is of great significance, and I suppose the second important value is recall score, since we like to predict whether a person suffer from diabetes or not. So if there are a great amount of people actually suffer from diabetes, but we did not collect them or predict them correctly, their health condition, will be extremely serious. So I suppose that's why this score is pretty important. So let's run the code and see the result. The accuracy is about 76%. The precision is about 61%, and the recall score is about 60%. Actually, the accuracy score, I mean, is satisfying enough, but I suppose the recall score still need an improvement. And also to generate a criterion equally reflecting the influence from precision and recall, we import a score named F1 score. So it seems that F1 score is 61%. It is okay, but not satisfying enough. So after our formal discussion, we comes to this decision tree part. Well, actually, decision tree, actually, decision tree is a classifier aiming at generating a series of reliable decision criterion under different circumstances of different features. And to put it more bluntly, the reason it is called a tree simply because each time it conduct a decision criterion will lead to the split of current dataset into two or more parts. And vividly speaking, it will generate two or more maybe branches of choices, and in the end, the amount of in the end the amount of all these the branches of choices altogether just seems like a boosting tree. So that's why it is called a decision tree model. Actually, I suppose the core issue within this model is loss function. Simply because each optimized decision step or each optimized decision strategy is based on the criterion to guarantee a least increasing in loss function. So since the loss function always presents a form of information entropy function, which is almost merely concerned with the probability rather than the actual value of each variable, we tend to use the original data set to deal with this problem rather than the normalized data set to deal with this problem, because there's nothing to do between this value between this model with the mean Euclidean distance within a data set. So if we can employ the origin set, it will be more easier for us to understand the decision criterion or the decision strategy in every leaf node, which is in every time to decide left or right, just that kind of thing. So since it is still classifier, we need to import this model from sklearn.tree, this package, and in order to reflect some of its important parameters, we still need to import another two plotting packages. And here comes the issue. If we always obey the criterion we mentioned before, that to guarantee least increasing in the loss function, in the value of loss function, without any restriction, without any penalty, there will be unpleasant. There will be an unpleasant phenomenon named overfitting. Overfitting just refers to a kind of phenomenon that this the model trained by this training set cannot generate generalizely generate good prediction on other data set. To be to put it more bluntly, also another times, it is just because in this train set, our machine comes up with a too specific decision criterion that it can merely adopt the slight characteristics of the training set rather than other part of the origin data set. So in order to avoid this phenomenon, we need to do an activity named pruning. So the strength of the strength of the pruning, the strength of pruning is actually determined by a parameter named CCP alpha. If CCP alpha is pretty large, we tend to get rid of more insignificant nodes, and if this if the number of CCP alpha is small, we tend to get rid of maybe just very little number of insignificant nodes, insignificant decision criteria. So under this circumstance, after we split the train set and test set, and generate an instance of the classifier, the first thing we need to do is not to phase model, but to model the pruning path of this model, to model the pruning path of this tree. To be more specific, to generate a possible sequence of CCP alpha within this within this condition. So we indulge CCP alphas as a variable CCP alpha. Actually, it is an ND array, and we just draw the tendency. It varies from 0 to the highest value and show it. It seems that most of CCP alphas are concentrated within the interval between 0 and 0.01. Nearly a few of them are pretty large. So after that, we need to select the best decision tree model under different level of CCP alphas. The fitting actually, the fitting process is pretty simple, but we need a loop to figure out the basic maybe accuracy score under different level of CCP alpha. So that's why we write these blocks of code. Firstly, we generate an instance for each level of alpha and feed them with training set, training x, training y, and after that we test, we evaluate the performance of this model on the test set and get the accuracy, and After that, store all accuracy within a list. So that's what we'd like to do. Finished. Uh, Here I need to find the highest the highest accuracy score. It is the 40 is the 40 is so the 40 is, and we need to report the score. Score is 76%. 76% is satisfying enough. So let us draw the overall condition of this tree. So we can see this picture. We just draw this tree by this block of code. It is pretty easy to understand. That's by this function. So after that, we finish our second model. We discussed what this decision tree is. What do we need to do to process data? To select parameter and to pruning the insignificant nodes, insignificant criteria, decision criterions. So that's basically a typical a series of typical procedures we need to do facing a decision tree model. And after that, we come to our neural network. Then we come to the neural network part. Well, actually, it is a little bit difficult or challenging to explain or describe neural network because it is pretty abstract, and also complicated enough. To deal with this issue, I decide to introduce you from two perspectives about this model. The first perspective is about its name and purpose, and the second perspective is about its contents and mechanisms. Well, actually, first, we will look something about its name and purpose. As its name suggests, a neural network, an artificial neural network um, aims at establishing a model or forge of human neural network to model its mechanism of decision, including classifying or regression, including predicting the discrete and continuous variables. So that's the purpose. It was this model would like to reach, and to reach this and to in order to reach this purpose, we need to understand its mechanism. So what actually happened within your network? Seriously speaking, we do not know what happened in each step of the neural network. We cannot say the parameter, but we still understand what kind of maybe what kind of operation actually happened during this process. That's why uh, maybe it is kind of unsupervised machine learning model. We still can adjust the value of we still can adjust the value of parameters to finally come up with a satisfying model. So I prepared several graphs to tell you the mechanism within the neural network. So just look at the left one, graph A. Well, actually, neural network consists of several layers of neural nodes, which actually means which actually refers to this kind of small circle. They are neural nodes. First, we input data into the first layer of neural nodes, and within each neural node, there will be a data. There will be a data proposal. There will be a data process or data disposal, which I will mention later. After that, it will conduct several, it will conduct a regression and send the regression to each node in the next layer, and all other nodes in the same layer just do the same thing. So in the second layer, each node receives in this graph, each node receives five actually independent variable, and it tends to make another kind of make another linear regression, and separately send the result to each layer to each node in the next layer, and repeat until the no until uh, until the last layer where there is merely one node, one neural network, no, one neural node to output our final result and prediction. Actually, this graph just this graph just models the mechanism of saving and delivering signal within our brain, within our body. But the only difference is that the atom or the element it sends, it sends or delivers its data rather than no signal. So let's come back to our code part. Since it is, since neural network consists of a group, a great amount of linear regressions, it can suitably deal with any linear classification problem. But in order to have a also satisfying performance on all non-linear classification problems, we need to do some adjustment to each neural node, which is we need to add a function uh, on certain non-linear characteristics, which whose name is activation function into every node to dispose the result of regression and send the disposed result to the next layer in order in order to guarantee its adaptation on non-linear classification problem. Very famous. There are several very famous activation function. Uh, for instance, ReLU, just REAU. I mentioned here, and sigmoid. I mentioned here, but also in the and also in the former part in our logistic regression. Well, actually, nowadays, ReLU is is most frequently used because firstly, it is the process of its calculation is pretty simple. It won't cost a good amount of time like sigmoid, and it also could deal the overfitting problem to some extent. So here comes another issue: overfitting problem. Neural network also comes up with overfitting problem if there is no penalty or restriction in the training set. So why this kind of overfitting problem finally comes out? It's simply because it is because um, in each step in each neural node, we tend to employ all training data to generate or to generate several regression results. So if in all neural nodes in, if in all neural nodes we employ the whole training data, the whole training set of the data, there will be a kind of overfitting problem because we uh, actually just come up with a kind of decision rule that is too specific. In order to avoid this kind of condition, we apply a technique named dropout. Uh, it simply means within each neural network, within each neural node, there is a probability it might be discarded. It might be discarded. So uh, if it is discarded, um, we just comes out a randomly different neural network. and not all data will be repeatedly used again and again. So that's what I would like to say, and maybe um, oral explanation is not enough. So I also prepare another graph, and I suppose you have already seen it before. That is graph B. This kind of neural node with a cross in it is a neural node is a group of nodes that we decide to discard according to the probability the probability we predetermined. So actually, mm, this kind of model will suffer less from overfitting problem, and the reason I you know and the reason I just say redo as an activation function will bring less overfitting problem is that redo things like this one can sometimes sometimes comes out uh, the value of y as 0 to some extent, um, or under this circumstance, it equals with that of it equals with a certain condition that this neural node does not output anything. It's just like another kind of dropout. So that's why we need to add activation function and dropout into our neural network. And then I will try to fit a neural network. I will try to establish and fit a neural network. First, I import some uh, important element of neural network from Keras. Keras is convenient enough because it is pretty uh, we now need to touch um, a great amount of very basic issue within this area. We just need to give it some specific value of the parameter. So firstly, we generate a sequential in order to load all the layer and drop out. We would like to add into this model. First, I qualify a layer of 200 neural nodes, and the activation function within each node is relu, as I said before, and each neural node accept actually accept an input with shape 8 commas, which means each neural node accepts the input of data with with 8 individual or independent variables, and then we come to the dropout. Uh, this kind of dropout is this kind of dropout decorates the first layer, which means that each neural node within the first layer owns 0.15 probability to be discarded, and then we generate the second layer. The second neural layer also contains 200 neural nodes, and during this node, the activation function is sigmoid, as we mentioned in the logistic regression. I believe you're pretty familiar with it. And after that, we also add a dropout technique to the second layer. The neural node, each neural node within the second layer also owns 0.5 probability to be discarded, and then it comes and then we come to our final layer, the last layer, or the output layer. Uh, and through the second layer to the output layer, we qualify the activation function as review again. And after that, we add all those layers and drop all techniques together by a compile method. So here we qualify the loss function as binary cross entropy. So just a very typical, a very typical information and entropy loss function, just as one we used in decision tree, and we report the accuracy as a score, the accuracy as a score or a criterion to test the performance of the model we will train later. And same procedure, we got X and we normalize it. We split the test and train set and we fit it. Uh, there are several parameters I'd like to know. I'd like to have a brief explanation. First, epoch. It's just like another version of iteration, and validation split is to guarantee how how big a data set we will have to validate the data, to validate the model, as we mentioned before. This is optional, but it could significantly enhance the credibility of the model, the parameter finally produced by the model. So let's say how it works. It might take several seconds, since there are 100 epoch of called iteration. Yes, so it reports the result of each epoch. Oh yes, the parameter variables just decide whether or not you will print the result of the result of each epoch in the console. We just print them out to better supervise them. So actually, finally, we got accuracy of 0.72 in the validation set. All right, and then we will test its performance on the test site. The accuracy, well, actually, it's okay, but not very satisfying. Not very satisfying. So finally, we report. Yes. So maybe this so according to this model, maybe we still need a further adjustment or polishing.